So here we are. This week we're going to start our module on data structures. This is going to be a very fun and exciting module, in my opinion. I think that this is when we go a little bit deeper. We learn about some of the I would say core aspects of computer science, and you get to see how much you've already learned already, and how the things that you've learned can be applied to some of these more complex topics. So data structures, right? Take a moment, go into the Q&A thread, and tell me what you think about data structures. What do you think a data structure is? What do you think? And maybe give me an example of a data structure that you think you've used already. Some people have used linked lists already. Some people have used you should all have used dictionary and list or array. Tuple. Yeah, data structures are a way to organize data. If there's a nail, or rather, let's say, if you want to hang up a poster in your home or a piece of art, maybe you'll have obviously the frame, and then you'll likely have a nail, right? So what tool do you use to place the nail into the wall to hang your painting? A hammer. Hammer makes perfect sense. But yeah, a rock would work. What else would work that isn't a hammer? A clog, sure. Glue, nail gun, yeah. So basically there's more than one way to skin a cat here, right? You have this ultimate goal of placing a nail into a wall in a way that's sturdy enough to support a piece of art. But you can use a hammer, you could use a rock, you could use a shoe, you could use a frying pan. They can get really creative here. But oftentimes there is a better solution, right? Out of the sort of myriad of ways you can place this nail into the wall, there's oftentimes the best way of doing so, right? There is the tool that best fits the problem that you're trying to solve. And that's something that I want to dive a little bit deeper into when we talk about data structures, right? There are so many different types of data structures. You've got your hash tables, you've got your arrays. So for the rest of this lecture, I'm going to refer to the Python list as an array. We touched on this very early on, that they are one and the same. The major distinction between a Python list and a standard array is that a Python list is implemented as a dynamic array. Obvious question would be, what is a dynamic array? Well, a dynamic array is an array that resizes itself to fit new to fit the new content, to fit the new element, basically. Right? Whereas in many other languages, once you've set an array of a certain size, you have to manually resize that array. Whereas with a dynamic array, you don't have to tell Python to resize. It runs a special algorithm to determine when it needs to resize. So basically, when it starts to fill up, it knows that it's filling up, and then it makes its capacity bigger. Right? So the length will be of, say, size X, and its capacity will be of size Y. Anytime X and Y get too close together, it makes itself bigger. Right? So if you imagine I don't know, like buildings or homes that could resize themselves to fit their occupancies. It's almost like a room requirement if you're familiar with Harry Potter, where it'll change itself to fit the need. So let me know if you have any questions on that, and of course, Slido is an option. Okay, so we've got arrays. Arrays are something that we're familiar with. Hashes are something that we're familiar. Sorry, dictionaries are something that we're familiar with. And then today we're going to talk a little bit more about a new data structure that is under the category of an abstract data type, an ADT. So it's similar in concept to object-oriented it's connecting the concept of object-oriented programming with this concept of data structures. All right, so you're building your own data structure, leveraging class definitions, so that you're able to create a tool that best fits the problem that you're trying to solve. Before we get into that, though, there's this, I've been throwing around the term like best. How do we in computer science determine what is best? Whether one sort of piece of code is better than another piece of code, or whether one implementation of a solution is better than another implementation of a solution, or whether an algorithm is better than another algorithm. Speed, like how fast it is, like it's all we care about in this computer science world that we're living in right now. It's not necessarily the implementations or programs that win aren't necessarily the ones that are easiest to read, or the ones that have the best variable names, or the ones that are just sort of the most interesting. It's all about whose code runs fastest, right? So there are different ways to measure time in regards to programming. Yeah, Pedro, you've got it. Jay, you've got it. Devin. So the different ways to measure efficiency in computer science. In theory, you could import a timer into your program. So Python has a timer module that you can import. And then you can start the timer right before a function, and then end it right at the end of an execution of a function, and then calculate that delta, and then figure out how long what the elapsed time was to run a specific function. That's all well and good. There are some inherent issues with that, unfortunately. So for one, with the timer approach, you don't get consistency, right? The runtimes you're going to receive are going to vary depending on the type of algorithm that's being used. It's going to vary by the type of implementation. So if I create a function to calculate that translates temperature in Celsius to Fahrenheit, and I do it in one way and you do it in another way, we might get different times, even though our solutions could effectively be the same, right? Because there's only one formula, and so there's only one formula, but you might have implemented it in a different way. You might have used more variables, or you might have done a few more operations than I did, and so we're going to lose out on a bit of consistency there by algorithm implementation. And then if I'm using a really old computer, and you're using a really fast, brand new computer, the runtime is going to change. It's going to vary as well, because based off of the computer. And then again, the runtimes aren't going to be really easy to predict based off of, say, really, really small inputs. And so that variability makes the timer approach bad. It doesn't make it the best approach for determining this relationship between the relationship between time and like algorithm or or program. So another approach would be to say count operations, right? So looking back at the example that I mentioned, might have written it here. So looking back at the example I mentioned, if I wrote a definition for translating degrees in Celsius to Fahrenheit, it could look something like this, where we're returning the Celsius temperature multiplied by 9/5, and then we add 32. All right, so who can tell me how many operations are executed in this command here, in this function? Okay, some mixed answers, but the right answer here is 3 in my opinion. We have multiplication taking place, we have division taking place, and we have addition taking place. So those are 3 separate operations. Oftentimes, the assumption is that mathematical operations, I'll write that down. Comparisons. So anytime you're trying to compare one number to another number, assignments, when you're trying to set maybe a list or an array equal to another variable, and then any sort of memory access. So oftentimes those are considered separate operations and are used in the count. Right? And so hopefully that example makes sense to you. And obviously the goal here is just to be able to evaluate different algorithms. And so the question here is, can we do that by just counting the different operations that are taking place? And the answer is kind of, sort of, but not really. It's a better approach than using a timer, but we still have some dependencies. We're kind of dependent on the algorithm. If like one algorithm versus another algorithm could be very difficult to compare. There's no sort of standardization, right? So, if like maybe you don't use 3 mathematical operations, or maybe you use a separate assignment, and then therefore like the count increases or decreases. And then, so we're dependent upon the implementation, and then we're still, but the good thing here is that we're sort of computer independent, right? So whether you've got a, whether you have a fast computer or a slow computer, we should still be able to have the same operation counts, assuming that we have the same sort of algorithm here. If you're also multiplying like your input by 9/5 and adding 32, we should be good to go. But there's still like no clear definition as to, which operations to count, right? Like, like I said to you just now, mathematical operations, comparisons, assignments, so on, are oftentimes thought of as operations that are worth counting to determine efficiency. But if you didn't know that, then how could you accurately convey to me what the efficiency or time complexity of your approach is? So we need some sort of common language. And so, the thing, another good thing here is that count varies for different inputs and can come up with like, and help us come up with this like relationship between, the inputs and the count. So like, regardless of how large C is, we're gonna get like the same count in terms of the same mathematical operation count. Whether I'm passing in 100 degrees Celsius, 1 degree Celsius, we're still gonna do 3 mathematical operations. But there's a much better way that than using a timer, than using a sort of like an operations counting method. This sort of new way, the standard way is this is what we call big O notation. It is the sort of standard method of communicating runtime efficiencies of algorithms. This is the language that computer scientists speak. And big O, like O is a Greek letter essentially, and it's written out like this, essentially a big, right here. So big O, that is a big O, and then some sort of function that describes how an algorithm runs effectively. So there are different classifications for big O notation that are used in these descriptions. But before we get into that, I want to take a step back and make sure that we're kind of level set on what our objectives are. I wrote it all here, but haven't mentioned it. So this is going to be part 1 of our discussion on data structures. We're going to talk about runtime complexity, which is what we've been talking about since we started. Then I'm going to go into linked lists a bit, and then if time permits, maybe talk about queues. And the key objective here is just that is to help you understand that there are appropriate tools to use for certain problems, right? So once you have a firm understanding of the job to be done, you need to reach into your bag of tools, your understanding of data structures and the trade-offs of specific data structures to determine which tool is the correct tool for your specific problem. And some questions here that some of which I've already posed to you. What data structures do you know? We talked about arrays. We talked about dictionaries. And what are they used for? I think many of you were on the money when you said that these are ways to store data, but it's also more than that. It's ways to organize data. There are ways of efficiently accessing stored data as well. Yes, data structures like all more or less do the same thing. They allow you to put data in and get data out, but they all do so in various different ways. And those are those trade-offs that I mentioned, right? So the way a list works is different from the way a dictionary works, and therefore, once you understand the differences, you're able to properly determine whether you're supposed to use a dictionary or a list. We talked about the timer approach. We talked about the operation counting approach, and we're diving a little bit into the runtime complexity, and the question of like why it matters, right? Well, calculating the speed of algorithms totally matters because computer science is essentially applied math of computers. We're trying to solve these real world problems with the aid of computers. And so if you're trying to build software, for example, for the healthcare space, and maybe this is like EHR software or electronic health record software, or maybe it's the software that's powering a ventilator, right? And so if you're your code doesn't run efficiently, then lives could be lost. If your code doesn't run efficiently, the computer upon which the program is running might crash. I'm sure all of you've experienced buggy or sort of inefficient software, like an app that crashes, or just like software that just doesn't run as expected when it's overloaded with new data. Maybe you've seen it in social networks, or maybe you've seen it in really popular websites, or during product launches when you're trying to pay for something online. There's like a really popular skate brand called Supreme, and they only make a limited run of certain products. And so when they release a new product, people race to the internet to purchase those products, and oftentimes like websites crash. Right? And so like that's kind of an example of what happens with a high load, high input load. And so it's key to, as a programmer, to take efficiency into account. And what the big O notation allows us to do is communicate, essentially, like it's used in communicating the worst case scenario, right? So if you are building software for the healthcare space that where lives are on the line, you're able to develop a program and communicate that, in the absolute worst case scenario, when we are dealing with, an arbitrarily large input, my code will still run in X time, right? And we'll talk about what X could be momentarily. Those are going to be the classifications of different runtimes that I mentioned earlier. And then there are also some other means of communicating efficiency. There's big omega. There's and there's another one that's escaping me, but you don't need to worry about that now in case you do come across it. The idea here is that the time that an algorithm takes, depending on certain inputs it receives, can be graphed, right? So if you've ever taken an algebra course or even a calculus course, you might be familiar with the different types of graphs. You might have a line, a linear graph, or a parabola in a quadratic graph, or even you might be familiar with the way the graph of a logarithmic function looks. And so what the sort of the big O notation is all about is communicating an upper bound for that graph. That saying that basically you're trying to say that no matter how big the input gets, the graph isn't going to exceed a specific level. I'm gonna take a stab at drawing on my screen here. I'm pretty concerned about it, honestly. Okay. So hopefully you've seen graphs before that look something like this. This is what we would call a linear graph. And it would be of the form f of x equals x, right? We can go into more detail about that momentarily. I just wanted to kind of finish off that thought. So, some of you might be thinking, okay, like why does this matter? It matters because when you're trying to determine an answer to a programming problem that you're trying to solve, you need to ask yourself, is this the most efficient way of solving that problem? Because oftentimes your initial sort of thinking is going to be wrong in terms of efficiency, right? You're going to think like, oh, I need to okay, so let's say the problem you have that you want to solve is it's like you're in a social media scenario and you want to see how many friends Jordan and I have in common on Twitter or something like that. How many followers we have in common. And so maybe you want to look through all of my followers. For each one of my followers, you want to like see if they exist in the collection of Jordan's followers. That, for example, is what we communicate as a big O of n squared problem. We could dive a little bit deeper into why that is, but effectively, if I have, say, 5 friends, and for each of my 5 friends, you're going to look at Jordan's 5 friends, then in the absolute worst case scenario, when you have to look at 5 people for each one of my 5 people, that equates to 5 times 5 operations. So 25 operations, which is why it's a quadratic relationship. So as these inputs increase, as the number of friends, as the number of like my friends and Jordan's friends increases, and we have to run that operation, run that algorithm, the time is going to increase quadratically, proportionally in a quadratic relationship. Hopefully that makes sense. And if it doesn't, please add some comments to the thread, and I'll try to come up with some better examples. Yeah, so there's more than one way to skin a cat when it comes to solving a problem, but the way you determine which approach is best is by analyzing the efficiency of each approach. All right, cool. So the topic of big O and runtime efficiency is pretty deep and complex. I think we can just revisit this. For me personally, it took quite a few examples over a long period of time for me to like feel fairly comfortable. And I think that you'll get it over time. But really quickly, I'd like to sort of dive a little bit deeper into some of these classifications. So these classifications or orders of growth are what are used to evaluate a program's efficiency when an input is like very, very large, right? So we're not really concerned about how long a program takes when you're dealing with an input size of, say, like 1 or 10 or 100. We're talking about an input size of like Google scale, right? When you're trying to calculate, crunch data for billions of users. And the goal here is to express the growth of a program's runtime as the input size just it increases, and we're ultimately trying to communicate that upper bound, that sort of like worst case scenario, right? And it's not supposed to be precise, right? It's not supposed to be an exact function that says like, okay, like this is sort of the mathematical model for my algorithm. It's really trying to say that my algorithm has its own mathematical model. We can go and manually count the operations of my algorithm like we did in that other example, but at a high level, my algorithm is similar. Like the runtime of my algorithm will never exceed like this upper bound here, right? That my temperature function is going to be my temperature function isn't going to sort of exceed a certain sort of threshold. Okay. And okay, so we're not counting exact steps here. We're really trying to I don't want to get too deep in like in the woods with the math concept, but if some of you might be familiar with the concept of an asymptote, essentially like a limit or boundary that a function gets really, really close to, but never actually touches. And so when we talk about big O, we're talking about asymptotic complexity. We're trying to find the function that best matches the behavior of an algorithm, whatever algorithm in question, and fits it asymptotically. So we're saying that, you know, like this, whatever ends up being inside of this in these parentheses here, maybe it's n, maybe it's n squared. We're seeing that this behavior is that upper bound, not that our algorithm is that. We're not saying that the algorithm runs in n squared time. We're saying that our algorithm is essentially best fits n squared time, but n squared time is the worst case scenario, right? So if we're dealing with crazy high inputs, then we'll get really, really close, but might not even touch n squared time. Right? And when you're calculating and maybe when you're going through an algorithm and trying to actually count the mathematical operations and trying to get to a count using these rules, you'll potentially find yourself with other constants, right? So a good way of thinking about it is looking at, say, another example. I'm trying to think of a good one. So let's say you wanted to add 5 to every number in a list. All right, and you're going to take in a list. And so for x in range of, actually, just say for x in list, we could do something, right? Maybe that's adding 5, right? So the fact that we're going to have a list of some size, say, we have our list and we have 5 elements in our list. And, maybe for this function add 5, we're going to add 5 to every item of our list. In order to do that, we have to visit every single element of the list, right? So just to gauge how people are understanding this, if I asked you what the runtime complexity of add 5 is, what would you say? Okay, so some of you are saying big O of n or linear. My question now is why? Yeah, it's because, so Alex, you got a really good explanation there, because the time complexity is directly related to the amount of data that we're going through in the list, right? So if we were to say that this function runs, that it takes like, say, 5 seconds to run, this is, oh, I think someone needs to mute themselves. Just to sort of just to sort of, not exactly play devil's advocate, but just a quick thought experiment here. This example that I have right here on the screen, it'll take us 5 seconds to run and add 5. to each one of these elements, right? So if I doubled the number of elements, and now we have 10 elements, how long do you think it's going to take in this made up example? Yeah, if we double the input, Eric's got it, then it's going to take us 10 seconds. And if we double the input again, it's going to take us 20 seconds. You know, that's what we mean by a linear rate of growth versus a scenario in which we have constant time, right? So if we have a constant time scenario, it doesn't matter how big the input size is, right? It's always going to take the same amount of time. So it would be in this example, this is not how this example would work, but if I were to tell you that, you know, an operation is constant, then it means that no matter how big the input is, it's always going to take that exact same amount of time, right? If it's linear, that means the time's going to change, but it's going to change depending on how much the input changes. So if it changes by, if the input doubles, the time doubles. And so it's a bit more, it's easy to predict, it's easy to calculate. But there are instances in which, you know, the time doubles, I'm sorry, the input doubles, but the time increases by x squared, right? So that's a pretty dramatic change, right? And then there are other examples where maybe it could be an exponential change in growth. Awesome. So quickly bringing it home to some examples from your last project here. So you had a set of commands in a list, north, south, east, west, all in a sort of all clustered together here. And let's say someone wanted to find the command at position 1, which is south here. That is a constant time operation, right? Doesn't matter how large commands is. It always takes the same amount of time to find an element at a specific index. Very similar to dictionaries. So maybe you had a dictionary of rooms, maybe a room called outside that mapped to a room object, and so on and so forth. Again, if I wanted to find rooms of outside, it would take the same amount of time as if I tried to find a different room in my dictionary. It's pretty similar in the sense, it's really similar in that sense to lists, but in the back end, dictionaries sort of operate a little bit differently. They're implemented in a very interesting way. And there's a whole section on hash tables that will dive a little bit deeper into this, because there's some really cool calculation that goes into play that helps us get to that constant time lookup. Awesome. Okay, so I want to see here. See if I could drop a poly. Let's see how everyone feels about runtime complexity. Here, we'll do +1, or I think there's a -1. Oh, sorry, it's not supported in threads. But maybe you can give me a thumbs up if you feel okay and you're ready to move on, or a thumbs down if I've totally lost you. And if you want to be anonymous, feel free to do the same in Slido. I just want to get a quick pulse on how you're all doing with this topic. All right, and if you're giving me a thumbs down, please ask a question. Feel free to do that in Slido. We'll take we'll carve out some time to go through the Slido questions. Please try to make sure that your questions are fleshed out. Notice that sometimes I don't understand what the question is asking, so help me help you in that case. Cool. I think a lot of people seem to get it. I think there are some people that might need a better explanation, but hopefully, as we proceed, things might make a little bit more sense to you. Okay, so last example that I wanted to go over before we dive a little bit into linked lists is actually before we take a break and go into linked lists is searching for elements, right? So if I give you a list and an element, and I wanted your function to tell me whether that element was actually in your list, what would that time complexity be, in your opinion? Right, and so we can try. This could be an example here. And then the element could be 3. How would you describe? Yeah, it depends on the algorithm, but we've got the algorithm right here, actually. Search for element. We go then linear. Okay, cool. So again, like just to kind of bring it down a little bit, or simplify it a little bit. Yes, Jack, we only care about the worst case. So let's dive into that. So to simplify a little bit, let's say that it takes Python 1 second to visit an element in our list. So it takes the for loop 1 second. Of course, it takes far less time, but just for this little thought experiment here, how long will it take to run search element given the data I have on lines 40 and 41? Yeah, 1 second. Okay. So what if we're looking at 9? 3 seconds. Okay. And what about 15? 4 seconds. So hopefully those who aren't understanding runtime complexity are seeing how the time is changing depending on the input, right? So why it's linear is because we're having to, it's because of the number of operations that are taking place. So if we were to run this in Python tutor, it might be helpful to see and like really visualize what's going on. So let's see here. All right, so here we are, Python tutor, our old friend. I'm gonna run this on this and all right, so we're storing our list, we're storing the element, and then the function. Okay, so we have our list, we have our element that we're searching for, and here we're going, and so every comparison is an operation, right? So we're comparing to, we're comparing 15 to 3, no good. Now we're comparing 15 to 6, no good. Now we're comparing to 9, no good. 12, no good. And so that's 4 different operations, right? If our element was in the list, we could potentially have fewer operations, right? And so that sort of change is a linear relationship, because in the absolute worst case scenario, we have to visit every single item in the list, right? And so the bigger the list gets, the more operations we have to do in the worst case scenario. So if the list wasn't just 3, 6, 9, 12, but 100 million numbers, then we have to go through 100 million numbers, like, just to see if 15 is in there, right? Or if list got really, really small and it was just 3 elements or 2 elements, 15 not in the list at all, we could find our answer a little bit faster. And there are some other algorithms you're going to see that are a lot more complex. So another really interesting example that I read a while back and then had to revisit so I can retell it to you all is my understanding is that it's based off of something that actually happened. It's a comparison between carrier pigeons and the internet. So there was this company in South Africa that was complaining about their internet speeds. Right? So their internet service provider, their ISP, was absolutely terrible, and they made this big public, sort of prank or bet that they could deliver data via carrier pigeon faster than it would take the internet service provider to download a similar quantity of data, right? And so they strapped a USB to the pigeon, a USB that had maybe 10 gigabytes of data to the pigeon, trained the pigeon to go back and forth between two offices, and then also sort of like when the pigeon was left one office, left point A to go to point B with this 10 gigabytes strapped to its leg, they also tried to download 10 gigabytes of data from the internet, and lo and behold, the pigeon won. Right, really wild. So the question then is, how would you describe that relationship between, say, the pigeon? Okay, so if the pigeon was a function, right? Like, how would you describe that sort of runtime complexity? Another example is, let's say it took the pigeon 3 hours to deliver that USB that had 10 gigabytes in it. And what if I told you it takes the pigeon also 3 hours to deliver a different USB that has 100 gigabytes of data? Rava, you got it you got it. It's what we call constant time. No matter how big the data set is, the results take the same amount of time to process, right? So if I give my pigeon 10 gigs, if I give the pigeon 100 gigs, terabyte, it doesn't matter, because it's just gonna fly mindlessly from point A to point B, assuming no other sort of edge cases or factors. Whereas with the internet, in this scenario, this like South African internet service provider, they take more time to download like higher quantities of data. So if you have, I'm sure everyone has experienced crappy internet connections. So your experience is worse when you're trying to look at Netflix than when you're trying to maybe write a document in Google Docs, or if you're trying to check an email or write an email, right? The difference there is that high quantities of data take longer times takes a longer time to download than sort of like smaller quantities of data, and the sort of poor performance increases at a linear rate, right? So let's say every gigabyte slows the internet down by the same quantity, right? So 1 extra gigabyte slows the internet down 10 minutes. So then 2 gigabytes slows it down 20 minutes. And so that is a linear relationship. Whereas it would be constant if, regardless of how much data you're trying to download, it's always going to take, say, 10 minutes, which would be wild, right? So that's like a good sort of real world example of the importance of time, of being able to communicate runtime complexity and being able to compare it, and a good example of comparing the relationships between sort of a process and data and time. Sorry, and the data and time that's involved in that process. Cool. All right. I think it's probably a good time to take a quick break. Right. Please throw in any questions into Slido. As soon as we get back, I'm going to take some time to clear out Slido. So if you've got a really big pressing question, please input the question there, and we'll give it some attention. Timer here. I know that I was given a timer Chrome extension to use, but I completely forgot to download it for class. Okay, so 7 minutes. I'll see you all momentarily. Yeah, I'll minimize the screen so you can see just my notes, but you might not be able to read it fully. Okay, so cool. We had 2 questions. How does Big O help us structure our code better? Can you give an example in code? So Big O doesn't help you structure your code better per se. So you've learned about different ways of programming. You've learned a more sort of linear style of programming where you're just sort of like executing specific commands. You've learned a more maybe iterative or you've learned a different sort of form of control flow with for and while loops. Big O is essentially a way of communicating what's going on in your algorithm in terms of like space and time complexity, right? So in terms of like time complexity, runtime complexity, Big O is just all about determining whether, like essentially being able to say that like this algorithm here that I wrote, runs in this type of time, and therefore can be compared to another algorithm that that is communicated also in Big O notation. It's a common language, right? So that I write a solution, you write a solution. We can analyze those solutions and be able to compare, essentially who has compare and see who's got the best or most efficient solution. Otherwise, there's no sort of a key way of doing that. Like I mentioned earlier, the timer won't be really accurate. Operation counting won't be really accurate. But being able to follow the rules of Big O notation, we'll be able to say that like, okay, Sam wrote an algorithm that runs in Big O of n time. I wrote an algorithm that runs in, say, Big O of log n time. And so my algorithm would win essentially in terms of being the most efficient. And we'll talk about how the different sort of classifications are stack ranked against each other. Operations are not, so our operations called inputs. The operations aren't the inputs exactly, but the operations are essentially what's in theory being counted towards calculating the Big O function or determining the classification. Big O, again, it doesn't help you write better code. It just helps you communicate what your code is doing. Super quickly, log n describes an algorithm that halves the input. Right? So every time you run this algorithm and you provide like bigger and bigger inputs, the time that algorithm takes in proportion to the input is about half. Right? So we pass say 100 elements to this algorithm, and maybe each operation could take 100 seconds, but with a log n algorithm, it'll take half that, like say 50 seconds. So algorithms that you might be familiar with, binary search runs in log n time, because you're constantly taking your input, breaking it in half, and determining which side of the data set to look at, right? So a good binary search example is finding a name in a phone book. I mean, they don't really have them anymore, but like those big, giant, old school phone books people used to have. If you wanted to find my number in it, for like the city of New York, you'd look at like a massive phone book, because there are 8 to like close to 9 million people that live here. But my last answer is the B, right? So if you're going to take the 26 letters of the alphabet, go into the middle, and then rip it in half, like rip that phone book in half, just toss away the latter half, because that my last name starts with the B, and then I'm going to be in the earlier half of the phone book, right? So that you've already halved your data set, already cut your data set in half. And so you're going to continue to do that and do that and do that until you find me. Do you suggest checking out Big O tutorials to practice for the Yeah, I think it's going to be really important that you keep some of these concepts in mind when you do your sprint challenge. I did take a quick look at it. Definitely seems challenging. We'll dive a little bit deeper into some of those concepts that you're going to see in the sprint challenge a little bit later. But right now, I kind of want to lay the foundation here. Yes, you are going to be judged based off of how efficient your program is, and the way you do that. This isn't necessarily Big O that's, inspiring this new look into programming. Again, it's just a way of describing algorithms. It doesn't do anything to your algorithm. It's really going to be about like understanding operations and what's going on in your code, right? So if you're doing some sort of mathematical operation, some sort of comparison, data access, or assignment, that takes some sort of effort for the computer, for Python to execute. And so that is an operation, right? And then if you're doing those operations across an entire data set, that also takes time, right? And then if you're doing that inside of another loop, right? So effectively, if you're creating, say, multiple, like a loop within a loop, that takes a lot of time and will result in an inefficient algorithm. So another question here. So in short, yeah, definitely check out some tutorials there, but we'll keep revisiting the topic. I am lost. Sadly, that's not a question, but I feel really bad for this person. If you could follow up with maybe a specific question, that would be helpful for me. Try not to get bogged down in all of this. Big O, it's a notation. It's a way of communicating complexity, and that's all you really need to know right now, right? And it's describing how an algorithm is going to work when it's given a lot of data. At a really high level, that's what we're talking about here. Data structure, it's exactly what you think it is. It's a way of structuring data, right? So you look at a list, you look at a dictionary, they store data in different ways. They allow you to search and access data in different ways. And so they have different ways of structuring said data. Do not understand Big O. Yeah, I'm hearing you guys there. What should you shoot for to write code based on the Big O classifications? Yeah, in terms, so I'm assuming that here you're trying to get at like what are efficient classifications, right? So we have constant time. Constant time is the best outcome you could possibly have. But of course, it's not an outcome that you can always get when you're trying to solve a really complex problem. After constant time, we've discussed linear time. It isn't the second fastest, but based off of just things that we've talked about, is second fastest, and then quadratic time will come after that. So gold medal goes to constant time, silver medal goes to linear time, and then the bronze go to quadratic time. But to get into more detail, really it's constant time first, what is called logarithmic time next. So that's that sort of having, like cutting the data set in half sort of scenario that I mentioned earlier. And then roughly it's like linear time, linear rhythmic time, quadratic time. And these are things that we can talk about a little bit later. It's kind of getting a little bit more in the weeds. Well, yeah, like you should always try to write your code in the most efficient way possible, right? So really it comes down to making these trade-offs. If you can do more with less, you should. If you don't need to use a nested for loop, for example, a nested for loop, like a good rule of thumb, right, is like nested for loops equal quadratic time, which is like a big no-no, right? Like it takes, it'll essentially mean that when your algorithm gets a lot of data, it's going to take a really, really long time to process, because you've got, like, say, like two different arrays, and so for each item in the array, you have to go through these items, right? And so like for item 1 in this array, I have to process 5 operations, and then for this item, I process another 5 operations, and then here another 5 operations, and here another 5 You see, like that's that sort of like level of complexity. That's complex, right in and of itself, and hopefully you can kind of like see how that might work. And you can think about some like real world cases in which, like, real world scenarios in which, like, you're trying to do something, and there's like an efficient way of doing it and an inefficient way of doing it. We can talk about some scenarios later as well, or you can come up with some of your own and share them with the class. That'd be really cool. I don't know much about graphical GPU, so yeah, I mean, that's essentially what we're talking about. We're talking about, so big O is also used to describe what's going on in memory as well. It's what it's called space complexity. So it's like, as your program is running, how much space is being taken up, and how much space is being taken up in memory and RAM. And then here, when we're talking about time, we're talking about like threads that are running in your computer that are processing the different operations. And so, yeah, I would say so. There's a correlation. Cool. All right. So let's pause on some of this big O stuff and move more into the data structure camp. And you'll see how they all kind of like meet in the middle. You'll see that there's going to be some level of comparison that one will need to make between one data structure and another, and like, how do we compare? Like that's the big question. Like, how do we know what is best or which is better? I don't know if you've ever had like siblings, for example, and you had to share some treat, right? Like, how do you compare to determine that your treat is better than your siblings? Oftentimes it's like, okay, like this side of the cookie has more chocolate chips, ergo it's better. Or this is the bigger half, therefore it's better. When it comes to computing and algorithms, we determine better by time, right? Like, which one's faster? All right. So we'll revisit time complexity and all that a little bit later. But if you have questions, keep passing them into Slido, and we'll take another look at them towards the end of class. Okay, so we've got about 40 minutes left. The goal is to, well, I don't know if it says on your project that we were going to go through doubly linked lists, but I was hoping to do singly linked lists first. And if there are any questions, you can ask me, but they're pretty like implementations are pretty similar. Anyway, so data structures, fun stuff. So when you think about data structures, there are like two main classifications of data structures. There are what we call contiguously allocated, or we'll just say contiguous data structures, and then linked data structures, right? When I say contiguously allocated, we're talking about how the program claims memory in the computer, right? So, how are we claiming and partitioning out memory in RAM, right? And contiguous data structures do so by just like claiming one big slab of RAM for the data structure, right? So a key example here. So, oh, I wrote it already. Cool. So contiguous, single slabs of memory. The examples here are arrays, matrices, heaps, hash tables, which we'll talk about later. And then the other option is linked data structures. So these are like multiple distinct chunks of memory bound together by pointers. So some examples there are lists, linked lists specifically. Don't get confused again. We're like when I talk, the Python list is an array. All right, that's what we're talking about here. And before I said there was list, when I said list here, we're talking about linked lists. Hopefully you were paying attention when I explained the difference. All right, so linked lists are trees, and there's some other data structures, but you might not encounter them in Lambda. But if you're curious, the internet's your best tool to dive a little bit deeper into all of that. Okay, so contiguous data structures, linked data structures. I'm curious, like, what do you guys think? What do you think are some of the pros and cons? Like, why would you pick one over the other? Feel free to use the thread. Cool. I like what I'm seeing. It's definitely, memory is going to be key. Insertions, searches, like certain operations like that are also going to be really important as well. So when we're thinking about arrays, these are really special because we can easily access any item in the data structure using an index, right? So an array, again, is that example of the contiguously allocated data structure. We tell Python, hey, claim this amount of data, this amount of memory, store this data in that memory, and and then with arrays, it's just kind of a contract to the user, right? That provide me with an index, and I'll provide you with the data that belongs in that index, right? And then we talked a little bit about insertions and searching, and like the worst case, if I'm looking for an item in my list, but I don't know what index it's in, does anybody have any idea how I could potentially find it? Right, so I have a list with, say, some numbers in it, but maybe I'm using someone else's code, or I'm using some REPL tool, and it's asking me to guess a number in a list, right? Like, what would be the runtime of that? Yeah, exactly, Brent. Person's got it. Vito's got it. Yeah, because in the worst case, I have to go through every single item of the array in order to find my element, which exactly how we discussed earlier. And then also with deletions, if I wanted to delete an element in the array, in the absolute worst case, again, like remove an element in an array that like I wasn't really aware of, like I didn't have the index for it. Again, it would take linear time. And then also in most cases, if you wanted to delete an element in the array that you did know of, so if I wanted to delete the third element in the array, that also takes linear time in the worst case, because the programming language, so Python has to, in memory, shift all of the elements to fill that gap, right? So we can't just like have this like empty gap. We're going to then shift all the elements, and so that shifting, in the absolute worst case, could require us to go through the entire length of the list in order to reshow all the elements. So that's why deletions also take linear time. Okay, so linked lists. So unlike arrays, linked lists are really special because you can't access elements by an index. Like there's no concept of an index or a position. A linked list is essentially a collection of what we call nodes, right? So essentially little sort of like blips of data. And a good way of visualizing it is like so. Cool. So a node can be visualized like this. Right, so excuse my handwriting here. I only have a trackpad. All right, so this is a node. And so here we'll have a value. Maybe my value is 7, right? And then in this other bucket, we'll have a pointer to another node, right? So that sort of linking of node 1 to this other node 2 creates a linked list of nodes, right? So these are linked data structures. Every time we create a node, that node is stored somewhere in memory, right? Some random place in memory. And then when we try to, so we're gonna have information about the value and information about the location of the next node, right? And that's all each node knows. It only knows essentially its name or its value and where its buddy is located. Okay? So oftentimes a big benefit to linked lists is it has to do with memory, right? So you often utilizing less memory than you would be in an array or a dynamic array, right? Because again, like you have to predetermine how much space you're going to take up. Whereas with an array, with a linked list, you can kind of more easily like add new elements, remove elements based off of this sort of more modular structure, right? So we're just manipulating these little dots, these little nodes in memory. And so if you think about memory, almost like if you think about it like a giant Excel document, right, where there's like every cell in the Excel is a space for memory, is a memory location. And so we have like a node here, we have a node here, we have a node here, and then just by traversing from one node to another, you can figure out, you can kind of learn about all the elements within, say, this linked list. A good way of looking at it here. Okay, so this is a website called visualalgo, visualalgo.net. If you want to visit it on your own, it's a good place to visualize algorithms and data structures. So here we have a linked list that starts at 94. So within the list data structure, we essentially flag certain. So like I said earlier, the list is essentially a collection of nodes, and these nodes are a pairing of a value and a pointer to or a reference to another address in memory. Okay. But then within the list structure, we keep tabs on the beginning and the end of the list, because it will help us when we want to, say, add or remove elements to the list. Right. So let's say we wanted to search for the number 46. There, so don't blink. There's going to be a quick little animation here. Right. So we're traversing the list until we find the element that we're looking for. Right. The way in which we do that is by defining pointers to certain elements of the array, or sorry, of the list. Right. So let's see if we can backtrack. All right. So if you see here, we're first checking to make sure that the list isn't empty. Always really important to do. It's a good way of like checking any like that edge case of bad data, right? So that you don't have to go through this like go through your algorithm. You can just exit with the right answer immediately. I mean, in this implementation, we have this index, but I don't think it's not really necessary. In case like, well, actually here, we're just gonna return the index, but if you wanted to return a true false value or something like that, you wouldn't actually need the index. Yeah. So effectively, we are creating a pointer called temp, and it's being pointed to, we're pointing it at the head or the start of the list. You use temp so that with the, because if you move head, then you lose tab. Like because your head is all about head and tail. Just keep tabs on what the true beginning and the true end of your list are. If you move those unnecessarily, then you're going to be in a little bit of trouble. Right? So what's key here is defining a temporary variable called temp that points to, or what head points to. So head points to the very beginning, which is 94 here. And we're going to go through this loop. The condition is essentially while what is V? I missed that. But effectively, but usually you're looping through this while you're still within the list, and that's effectively the condition that you're trying to get at. Then, like assuming that you're still within the list, you want temp to go from head to the next node, and then from that, and then if assuming that that node isn't the node you're looking for. Oh, sorry, I see here. V is 46. So whatever the input is, so this is a search algorithm. So if we're searching for 46, and we're saying that V equals 46, and then while you're not at 46, keep moving, right? And in order to move, you're reassigning temp to other nodes, right? But again, you're not moving any pointers sort of that are inherent in that are like sort of like set within the linked list. You're just moving temp, right? So temp points to head, and then the next step would be for temp to point to the next node that head points to. And since temp points to head, you could say temp.next to get to the next item. And if it's not null, and null is usually used at the very end of the linked list. So here we have tail, and it's tail because its next node is null. It's the very end. So you're going to keep traversing until you either find B or 46, or you get to null, and therefore at the end of the linked list anyway. Yeah, that was a lot, but I'll quickly run through this animation again so you kind of see what's going on. Okay, so another example would be insertion, right? So let's say we want to insert an item in our linked list. I want to insert the number 84. All right, that was really fast. Let's see if we can do that again. Much slower. But effectively, we're taking this new, I'm giving this algorithm a value of 84. 84 needs to be first stored into a node needs to be created with the value 84. And that node needs to be connected to the rest of the list. And the way we do that is by creating a pointer from the node that we created, the 84 node, to what was the head of the list originally, right? And so if you look here, that's effectively what's going on. We're creating a new node. Here they're calling it vertex. Then the next node for the new node that we just created should be what is currently head, and then we're going to assign head to the new node that we just created. Cool. Let's see, another good example is removal. Okay, so here we're saying like remove the second item in the linked list. Notice how we don't have a big gap in the middle of our list, right? We've traversed from the beginning to the element that we wanted to delete. And then we changed the pointer of the previous node, right, which is 94. So looking at the pseudocode that we have here, if the list isn't empty, then we need to define a new node named pre, short for previous. Set it to the head, and then we're going to traverse the linked list until we find the node that we want to delete. And then we want to bypass that node, the node that we want to delete. And that's effectively how we delete it, by just kind of skipping over it. So then pre will now, so pre.next, so then the pointer of pre no longer points to the node to be deleted, but to the node after it. Hopefully, like, that makes a little bit of sense. We'll actually go in and implement this ourselves. So hopefully through that process, you'll feel a little bit more comfortable. Cool. So we've got about 20 minutes left. I'm just gonna power through and then maybe end 5 minutes early so you guys can have that bit of a break. Okay. Okay, so what you need to understand here is we've got two objects that we're using, well, two classes that we need to create. Because a linked list is kind of composed of two different structures: the node itself and the linked list, which is sort of the relationship between the nodes. Right. So first, we want to create a node class, and then in it, we're going to store, or we're going to want to pass a value, but sometimes we might not want to do that initially. So we're going to make that optional, and then there's going to be a reference to a new node, a next node. So like the buddy of the node that we're talking about. Yeah, I guess that's another way of thinking about all of this. It's the buddy system. All right, so the value of the linked list, sorry, the value of the node is value. And then the reference to the next node in the list cool, simple enough. But I think it's going to be really important to have essentially what's called a getter, a function that a method that allows us to retrieve the data within a node, right? So the key data that we're really storing here, which is the value. Right? So I know that you all have a sort of the skeleton of a doubly linked list, but right now we're working on a singly linked list. But you can use this as sort of a jumping off point or inspiration for filling out your doubly linked list. And we'll go through it together next class. Okay, so we have a way of getting the value. Obviously, next we're going to want a way of getting the node, getting the next node. Hope you're all following along. Okay, so now we have got some getters. Let's put together a set method. All right, so if I want to maybe change a node's value, or well, actually here in this case, we're going to want to change the reference of a node. So let's say I created a new node at some point, and I want to make sure that the current node that I'm working with points to this new node. I'm going to want this type of set next method. So self.nextNode is going to equal new next, right? So that's the example of having right, so maybe we have a node 84 and we want to insert another node, or we want to change this pointer, this arrow here, to point to something else. This is the method through which we're going to do that. All right, so that's like pretty much what we need to worry about in terms of the node itself. Now there are some really key helper methods for the linked list. All right, so again, a linked list is a collection of nodes All right, and what's really key about the linked list itself are, at least in the singly linked list, there are two flags that I mentioned earlier. Who can tell me what they are? Head and tail, exactly, right? So the linked list data structure, the linked list object needs to keep track of its head and its tail in order to fully function and work here. We need a reference to head, and initially it's going to be none. And then we also need a reference to tail, and initially it's going to be none. And so if I wanted to add, if I want to add to tail, what step should I take? Question for the audience. Check to see if the list is empty. Yeah. So I'll write that down. Okay, what next? Well, yeah, you want to create a new node. Right, so you want to take this new value and create a new node with it. What next? Solid responses. Yes, if the list is empty, we're going to end up pointing the head and tail to the new node, because we're going to start and end at the same spot. So thank you for that one, Jack. Next. Yeah, if we're dealing with a list that is not empty, yes, we will want to call set next on the original tail, and set it equal to, and then set the tail equal to the new node. All right, so let's give that a shot. So we've got, it depends. All right, so first we want to check to see if check whether there's a head. So here, if the list is empty, set both head tail to new node. All right, and so let's go ahead and do that. So self.head equals new node. Oh, we haven't created a new node. So maybe the first thing we want to do is actually create the new node. Because no matter what, we're going to output, we're gonna do something with this new node. Hopefully that makes sense to you all. So now let's create new node. Set that equal to node of value, and then pointer none. All right, so going back here, if there's no head, we're dealing with an empty list, then we're going to set self.head of our list equal to the new node. We're also going to set the tail equal to our new node. Cool. So yeah, like the question now is, what happens if we're dealing with a non-empty? What happens with a non-empty list here? Oh, yeah, Ethan already had it. We're going to want to set the current tails next reference to our new node. So self.tail dot set next is going to be, sorry, new node. So that means in this example, we have the tail here at 46. We wanted to add to the tail. We could do all right. We're gonna want to change the reference to the tail. We're gonna want to change that tail reference. So set next changes. So now our last node will now point to this new node as opposed to pointing to none. That's step one. And then step two is that our self.tail will now be the new node. Right, so we saw it momentarily, right? So here, tail is still 46, but this is not the tail end of the list. That's essentially happening at that last line that we wrote. Right. So we've created our node. We've called set next on the tail node to create this relationship, and we've changed the pointer of tail from 46 to 80. Cool. So another thing that we might want to do with the linked list is we're going to want to delete things. All right, so let's say we want to remove from head. How would we go about doing that? Any ideas? Hint is very similar to what we did before. Move it to the tail. Not sure what you mean there, Jesse. Yeah, Ethan's got it. So if there is a head node, like 84, for example, and we wanted to remove 84, then we're going to have to make 94 the head node. but there's a specific algorithmic approach that we're going to want to take here. It's very similar to what we took earlier, right? So yeah, first you got to check to see, like, you know, what's going on with your check. You definitely got it. When in doubt, always check your input first. Always. So again, if not self.head, return none. See, solve that problem really easily. And then the next step is if head has no next, you know, what does that mean exactly? Yeah, there's only one thing in the list. You got it, Jesse. So then what we do in this case is, if not self.head.get, I know this whole like next and head and tail, like, gets a little confusing. But you know, if you try to get really focused on a specific example, or like write it out on paper, it's so much easier to keep track of things in your head. It's so much easier to keep track of things on paper than in your head. Self.head.get next. Then we're going to want to, we're running really close to time here. Then we're going to want to set head equal to self.head. We're going to want to get a reference to the head of the list. And then we're going to want to delete the list's head reference. So effectively remove the previous head. And then we're going to want to also make sure that the tail reference isn't referred to anything at all. Again, in this case, like it was likely referencing the same node, right? So if we're dealing with one element in the list and we want to get rid of that element, we're going to want to change both the head and the tail references. And then after that, you're pretty much done, and you can return head.getValue. Right, to essentially return that to the user so they, as confirmation that everything ran smoothly. Cool. And then another thing we could do. So otherwise, we have more than one element in our list, and so the next steps would be to change value. Set value equal to head.get value. And then we want to set the head reference to the current head's next node in the list. So if this is head in this list, and we want to set head equal to what is now the second place in the list. I need to write a little comment here to answer a question. Tail reference. Okay, so we've changed the value. Now we need to change head. So we're going to set set the head reference to the current head's next node. So that's self head.get next. And then return value. again, is confirmation to the user that everything ran smoothly. All right, so there's one more item, but there's one more helper method, but I'll drop the code right now so you guys can see that extra method. But hopefully this has helped you sort of see how list traversal works. It can get a little confusing, but ultimately you're using references to traverse the list, so that you're not changing the list unless you're for the traversal. But if you're going to do some removing or deleting, there's a specific way in which we do that. So I would do a lot of practice here. Create some linked lists, play around with them, add, remove, and see how that works. And then also play around with visual algo, so you can also get a firmer understanding of how list traversal works, because it's going to be really important. Going into our next topic on Thursday, we're going to finish this up. We'll look at doubly linked lists pretty quickly, and then go into stacks and queues. All right. If you have any more questions, feel free to, I think direct messaging me is probably the best next step. I'm going to take the next few minutes to look at Slido, but class is adjourned. You're not understanding the purpose of Big O and linked lists. Again, linked lists, we're talking about different things. We're talking about the way in which we describe what's going on with the linked list, which is Big O. And then we're talking about a data structure, a way of saving and structuring data linked lists, right? So well, some of the methods that we've created already, or even some of these cases here, when you want to insert or remove an element from the list, it takes a certain amount of operations in order to do that, right? So here in this case, to insert the number 80, to insert a node with the value 80, it takes constant time, right? So that means that regardless of how long this list is, inserting at the tail is always going to take the same amount of time. It's only that one quick operation, because we know where the tail is, we don't have to travel through the list in order to find the tail. And the same thing for adding at the head, right? So any of those types of insertions are pretty quick. But if we wanted to add something in the middle of the list, that could take some time, right? Because you have to travel through the list. And that traveling, right, the way we describe it in computer science, we describe it using Big O notation, where we say that operation, that loop that you have to go through, it takes say n number of operations, and n is going to be the length of the list. How do we know what a code's runtime is? Like I mentioned earlier, there are 3 methods. You use the standard method of Big O notation to describe it, and it's kind of an intuitive. Well, it's not intuitive, but it's kind of difficult to articulate. But it's a combination of it's a combination of math and counting operations, right? Or sort of estimating number of operations. You have a sense for you have a sense for the number of operations an algorithm will take based off of the elements within that algorithm. So if we have to, again, iterate through an entire collection, entire array or entire list, then we know that we're going to need n number of operations. N again is the length of that collection, right? So that's a sort of that's a starting point. But then obviously you're gonna have these other operations, right? So maybe you're adding a number, or you're setting a variable, things like that. The interesting thing about asymptotic complexity is that we drop or sort of do away with these operations that don't add anything to the most the highest order sort of element in the description. I know that was kind of convoluted, but you know, if you're counting your operations, and you know you have, like, say, an assignment, and then you have a loop, right? That assignment's going to be +1 in terms of operations, and that loop is going to be +n in terms of operations, right? And so you could say that you have n+1 operations, but we don't deal with constants when we just went in big O notation, right? It doesn't really matter, right? What really matters is the that main function that we're trying to describe, that main function that caps or bounds your algorithm, and that's going to be n in this case. So to answer your question, you're essentially counting operations, but with big O, you're doing it in a way that's a bit more structured. There's specific rules in place, right? To figure out what those rules are, highly recommend taking a look at, maybe some algorithm textbooks or any online resources. I'll try to dive in a little bit deeper into that in preceding classes, but in the following classes. But for right now, just know that mathematical operations, assignments, loops, and things like that, like those are operations that add to the count, and we're trying to describe how that, describe what's going on. Yeah. Do linked list queues and queues used in all programming languages, and how often are these used in the working world? Linked lists, queues, yeah, they're used. They exist in other programming languages. Just about all the ones I've worked with, and yeah, we use them in the real world. They matter. Again, you'll see that there's inherent benefits to using one data structure over another, and it really just depends on the problem you're trying to solve. What would be good real-world data to store in a linked list? Well, what you'll learn is that these data structures that you're learning about right now are actually there may be, okay, so the built-in data structures, like your dictionaries and your arrays, they're sort of like more low level, and then what we're dealing with now are like abstract data types that again require us to build out different classes and leverage like these relationships to build out something that's a bit more robust. But then you'll find out later on that even like linked lists can be an element of an even greater, more complex data structure. Right. So in terms of like what would be a good real world data, like what would be good real world data to store here, the answer just is it depends. You could use a linked list when you're trying to model like a graph or a tree, right? If you're trying to model hierarchies, trees can be really important, and therefore linked lists. What dictates adding the new node to the tail opposed to the head? The user will dictate that, right? And then also the interface the overall interface that you provide. Yeah, if I use a function that says add to tail, I expect it to add to the tail. I understand this, but I do not understand the significance of these topics. Significance of, sorry, I feel like I'm beating this whole big O thing on the head. Beating the dead horse or whatever the saying is. But you've been learning how to code, and that's all, and that's great. But the difference between writing code for fun and writing code for the enterprise, writing like actual software that people use, is efficiency, right? But that's why it's really important that you understand that speed matters. First and foremost, speed matters. And that you also understand there's a way in which people in the know, aka computer scientists, describe speed. That's big O, right? And so now we're entering in this world of efficiency and runtime complexity. And that's all in service of allowing you to understand the importance of efficient code and how to just talk about efficient code. That's the goal. If you have no idea what we were doing, you can send me a direct message. I can try to break things down for you a little bit. Talk to one of your leads. Please send this. Yeah, I'm going to send the Python files right now. That's bounced over my head when I tried to. I know this I guess I know I'm trying to push through this, but I also want people to understand, and it's really complicated. This is honestly like we're getting into what makes computing and computer science hard. But try to come up with like some specific questions, and then we can fill the gaps for you, right? Like questions are placeholders for answers. So come up with some questions, and we'll get some answers for you. Seems like a contrived example of a linked list. I don't know about that. It's just a linked list. It's not like a contrived example of a linked list. Linked list is a bunch of nodes that reference each other. How you use it depends on you. But like I said, trees, graphs, that's how we use linked lists to model those things. All right, everyone. Thank you so much. Signing off.